This video covers section 2.6. It's titled Moments and Centers of Mass, and section 2.6 is the last section that we're going to be covering in chapter 2. So this is again another application of integration, and if we look at the learning objectives for this video, the first thing we're going to learn how to do is find the center of mass of different objects in a plane. We're also going to talk about how to locate the center of mass of a thin plane. That's a typo there. That should say thin. And then the last thing we're going to talk about doing is using symmetry to help us locate the centroid in a thin plate. And when you're talking about a centroid, another name for centroid is the center of mass. So we can think of this as our center of mass. And that basically is the point on an object where, especially if we're talking about a plate, where that object would balance perfectly without tipping over on either side. And in order to find centers of mass, we need to first talk about what a moment is. So a moment is usually defined by the letter capital M. And we call that the moment of a system about the origin. And the definition of a moment is given right here. A moment is the measure of the tendency of an object to rotate about either the x-axis or the y-axis. And so we have two different formulas here. We have the moment about the x-axis, which is given by this formula, and then we have the moment about the y-axis, which is given by this formula. And you can see in figure 2.62 what we mean when we're talking about moments about a specific point. So if our rotation point is, say, right here where this triangle is in the middle, then the way we would calculate the moment is we would have to add up so if we want to talk about the moment about that fulcrum, we would have to take and add up the sum of the individual masses times their distance. So in this case, we would have d1, that's the distance that mass 1 is away from the fulcrum, times its mass, plus distance 2 times its mass. And that's going to give us our moment. And we need moments to figure out the center of mass. Down here at the bottom, again, the center of mass of a system is at the point where the moment is spread out evenly, or it's averaged across the area, which is, again, why it is the point where whatever that object is will not tip. It will balance perfectly. And so let's move on to Theorem 2.10 at the top of the next page. These are the important formulas that we're going to need to be able to find the answers to the examples and different problems that we're going to be working on in this section. And the main things you need to be worried about are these two formulas. These tell us again how to find the moments about either the x-axis or the y-axis. This is our x-axis moment here. It's a moment about the x-axis, and then this is our moment about the y-axis. Note that M is the total mass of the system. So that's what we're going to get when we add all the masses together. And then the way we find the center of mass, we call that usually x bar comma y bar, so it's just a point, is found, the x bar is found by taking the total moment about the y-axis and dividing it by the mass of the system. And likewise, the y bar is found by taking the total moment about the x-axis and dividing by the mass of the system. So example 1 is a nice simple example of taking these concepts and applying them to a system where we have a bunch of masses at different points. In fact, we have 3 different points and we have masses located at those points. The At the point, for example, 3, 2, we have a mass of 8, and so on for the other 2 points. So again, if we're going to find the center of mass, x bar, the center of mass, x bar, comma, y bar, we need to first know the moments. So let's go ahead and calculate those individually. The first one we're going to do is, let's do the moment about the x-axis. Moment about the x-axis. And again, the moment about the x-axis is you sum up the individual masses times their y distance from the x-axis. So if I start with mass 8, its y distance from the x-axis is this distance right here, and that is going to be 2. It's 2 units away from the x-axis, so this is going to be multiplied by 2. Remember, this is the moments about the x-axis, so all these distances are distances from the x-axis. And likewise, we could do this for each of the other 2 masses as well. This mass has a distance of 1 away from the x-axis, and because it's below the x-axis, we're going to call that distance a -1. And then mass 3 has a distance of +1 away from the x-axis. So let's go ahead and put these into our formula. So remember, it's a sum, so we're going to add the mass of 4 times its y value, which is -1, and then the other mass was 3 times its y distance away from the x-axis, which was +1. Let me write in those distances real quick here. So this was 2, this was -1, this was +1. All right, so hopefully that makes sense. We could go ahead and finish the math here on this one. This is going to be equal to 16 minus 4 plus 3, which gives us a moment of 15. And then go ahead on your own real quick, pause the video on your own, and go ahead and figure out the moment about the y-axis, if you will. Go ahead and pause the video. All right, welcome back. Hopefully you found that the moment about the y-axis was equal to 29. If you didn't, go ahead and go back and watch how we did the moment of around the x-axis again. These distances of 3, 3, this is because we have a distance of 3 away from the y-axis. This is our x distance in this case, whereas these were y distances. All right, so you get 29, and then we're going to apply these equations in 2.17 to find our x bar and our y bar. So this is kind of easy to remember because it's always the opposite. So x bar x bar is equal to moment about the y-axis divided by m. One thing we did not find yet is m. Let's do that real quick. So the total mass of the system is 8 plus 4 plus 3, which is 15. We don't have units here, so we'll just leave it as 15. And so x bar is 29 divided by 15. And likewise, we can find y bar, which is the moment about the x-axis, times the total mass of the system, which is 15 over 15, which is 1. And so our center of mass is going to be x bar, 29/15, comma y bar, which is 1. Okay? So 29/15, comma 1. 29/15 is almost at 2, so that center of mass is going to be right about right here. It's about, so it's 29 15ths, comma 1. That's the point where all of those three masses would balance out and there would be no tipping. So what about if we have a thin plate? Let's talk about that. So instead of like the last example, let's say that we have a really thin sheet and it's so thin that we basically treat it as a two-dimensional system. And whenever we have something like that, the mathematical term for it is called a lamina. We'll get back to this idea of symmetry here in a second. Let's go to our formula, or our theorem 2.12, which talks about how we find the center of mass for a thin plate. And it relies on us first having the graph. We got to have the graph. So much like when we found our areas and things like that, we're going to need to find the graph here. So we're going to have some function. Let R denote the region. This is important. Let R denote the region that's bounded above by the graph f of x and below by the x-axis. So notice R is this shaded blue region in here in figure 2.65. And it's also going to be bounded on the left and the right by the values A and B. This is another important thing. Let rho be the density. And so the way we're going to find the mass is we're going to integrate our function, which is basically, we know that the integral of a function dx from a to b, that's going to give us the area of this blue section. So if we take the density times our, this is basically the area. This is equal to the density times the area. That's going to give us the mass. Normally density is something like kilograms per cubic meter. Normally we think about mass as taking density times the volume. But remember, we said on the previous page, this is a lamina. It's so thin that we're treating it as a two-dimensional object. So the mass is actually going to be the density times the area. Now when you get into Calculus 3 or Math 230, we're able to deal with three-dimensional objects and finding the mass and using actually this formula. But we're not quite there yet in this class. We need to be able to have double integrals to be able to deal with that, which you'll learn about again in Calc 3. So the other thing we have here is it's a different formula than what we had on the previous page. For a thin lamina, here is your formula for the moment about the x-axis, and then here's the formula for your moment about the y-axis. We're not going to get into where those come from. If you're interested, though, you could read in the textbook. And then, of course, we have the same formulas for finding x bar and y bar to find your center of mass. So even though we have these formulas for the mass and the moments about the x and y axis and x bar, y bar, it requires a few different calculations to get there. And what you see down here below the theorem is you see some simplified formulas for x bar and y bar that actually combine the concepts here in this theorem. You know, theorem 2.12 combines them. And so we can just use these integrals to find our center of mass. Again, the center of mass is x bar, comma, y bar. So let's take a look at example 2. It says find the center of mass of a semicircular plate of radius 4. And so the first thing we want to do is graph a picture of what that's going to look like. Let's go, we weren't super specific about this. Let's assume, we know a semicircular plate is half of a circle. So let's assume that that plate is above the x-axis and it's radius 4. So I'm going to go ahead and number out here to 4. and then draw in our semicircle. So it's going to look like this. And remember, we need to talk about the area inside of that. Because that's needed in these formulas, right? You need the area. And we could find the area. We don't necessarily have to, though. Sometimes we can use geometry to make this work easier on us. So this is a circle. We know that the area of a circle is pi times the radius squared. Since we have a semicircle, it's going to be half of that. And so in this case, we have half of pi times the radius, which is 4 squared. 4 squared is 16 times a half. This area, this total area in red here, is going to be 8 pi. All right. So one of the things that we did not mention earlier is that when we were talking about the lamina, that we assume that the mass of the system is distributed continuously or evenly. So it says the mass of the system is distributed continuously across the thin sheet of the material. So we can use symmetry in our advantage to this one. Since the mass is distributed evenly, we know that in the x direction, it's going to balance perfectly because there's an equal amount of mass on the left side as there is on the right side. So we know it's going to balance somewhere along this y-axis, which means we can say that x bar is equal to 0 by symmetry. Now you could go through and use the formula above here to find x bar, but we don't need to. Whenever symmetry is on your side, go ahead and use it to your advantage. Now y bar, we are going to have to do that. So y bar is equal again to 1 over a times the integral from a to b of 1/2 times our function squared dx. And we know the area is 1 over 8. We know the area is 8 pi, so we have 1 over 8 pi. In the x direction, we know this integral goes from -4 to +4. So this is going to be the integral from -4 to +4. We have 1/2. And our function, this is something that you may or may not know, but when we have a circle, you know the equation of a circle is x squared plus y squared equals the radius squared. So in this case, the radius is 4, so this is 4 squared is 16. And then if you were going to solve for y, we would get plus or minus the square root of 16 minus x squared. 16 minus x squared. And because the top half of the circle, that means that we're going to use the positive square root. If it was the bottom half, we'd use the negative one. So this is going to be, y is going to be equal to the square root of 16 minus x squared. So that's that right there is what we're going to put in for our function, because that's what defines our area. And so this is going to be the square root of 16 minus x squared dx, and that'll work out nicely because the square root will be canceled out by the square. I'm going to move this 1/2 out front, so this gives us the integral of 1 over 16 pi times the integral from -4 to 4. We have 16 minus x squared dx. And now we can go ahead and integrate that. We have 1 over 16 pi. The antiderivative here is going to be 16x minus 1/3 x cubed. Integrating from -4 to 4. And this is going to come out to 16, do all the work, I'm going to leave that to you, but you should get 16 over 3 pi is your final answer. So that's your y bar, which means your center of mass is going to be 0, 16 over 3 pi. Now, if you're curious about the actual value of this, the 16 over 3 pi is about 1.7. So, I mean, we could think of this as about 0, 1.7, which puts it right about here in our object. There's our center of mass, 0, 1.7. And intuitively, that seems like a good balancing point. I hope you agree, of being a place where if you put an object, say a stick below it, it would balance evenly without tipping. Now, one other thing I'll just mention is we calculated the area using this formula. That we can't always use geometry to do that. So if we were to actually need to find the area, you're just going to use the concepts that we used in section 2.1 earlier in the chapter. Remember, in section 2.1, if we're going to find that area, we're just going to integrate from -4 to 4, and we're going to find the function, the area, by integrating the function, which in this case was the square root of 16 minus x squared dx. We actually don't know enough from integration yet to know how to find an integral like that. So the only way we could actually do this problem at this point is to use geometry like we did right here to find the area. Now later on in the class we'll learn how to evaluate an integral like this, but you will have problems in your homework and notes though, where you will, or I'm sorry, in your homework in your lab, where you will actually need to find that area. And I'm going to post the solution for example 3. We're not going to go over this in video, but it's pretty straightforward. You do have a new set of formulas here that you're going to use to find the center of mass, and these are the formulas for the center of mass when you have a region R that is defined as being between two curves, f of x and g of x. So of course the area then, if we were to find the area, that's going to be the integral from a to b of f of x minus g of x, that top button minus the bottom button, or the bottom function, top function minus the bottom function. Again, just like we did in section 2.1. And so you're going to want to start with graphing the region. You need to graph the region. Find the region that's bounded by those two functions. Again, I'll post the solution. Let me know if you have any questions. And that's going to do it for this video. So thank you and have a good day.